theorem, every countably compact metric space is second countable. We know that in a metric space, separability implies second countability. So, it is enough to show that every countably compact metric space is separable. Let XD be a countably compact metric space. We need to show that the space is separable, that is, we will need to show the existence of a countable dense subset in this space. Now, for each positive real number R, let AR be the subset of capital X, which is maximal with respect to the property that every two distinct points of it are at least at a distance or apart. The existence of such a set can be proved using Zorn's lemma. Now, we claim that the set AR is finite. If possible, assume that AR is not finite. Then AR is an infinite subset of X, where X is a countably compact T1 space. The space X is definitely T1 since every metric space is T1. So, AR is an infinite subset of a countably compact T1 space. By the characterization of countably compact T1 spaces, every infinite subset of the space must have an accumulation point. So, in particular, AR must have an accumulation point, say small x. But since X is a T1 space and since small x, the point small x is an accumulation point of AR, every neighborhood of the point small x, and in particular if we take an open board, say B x R by 2, these neighborhoods will definitely contain infinitely many points of AR. Hence, if Y and say Z are any 2 points of Bx R by 2 intersection with AR with Y not equal to Z, then the distance between Y and Z will be definitely less than or equal to d of yx plus d of xz using triangle inequality. And since Y belongs to the open ball Bx R by 2, d of yx will be less than R by 2. Similarly, since Z belongs to the open ball Bx R by 2, we will have dxz less than R by 2, and R by 2 plus R by 2 is in fact equal to R. Therefore, we have observed that any two distinct points from this intersection will be less than R unit apart, that is d of yz is strictly less than R, but Y and Z are members of AR also. Therefore, the distance between Y and Z must be at least at a distance R apart. So, dyz should be less than or equal to R, and hence we have arrived at a contradiction. Thus, our assumption that these sets AR is an infinite subset must be false. Therefore, we can conclude that AR where R is any positive real number is a finite set, as we have claimed earlier. Now, let D be the union over n varying from 1 to infinity A 1 by n. Then this is in fact a countable union of finite sets. So, D is countable. Thus, we have constructed a countable subset of the space X. Now, we are trying to show that this set D is dense in X. That is, we need to show that D closure is equal to X. For this, to prove the denseness, it is enough to show that this set D intersects every non-empty open subset. Let Bxr be such a ball. Now choose an n such that 1 by n is less than r. Such an n will definitely exist since r is a positive real number. If r is very small, then we will have to choose n sufficiently large. If Bxr intersection with a1 by n is empty, then if y is any point of the set a1 by n, then d of xy will be definitely greater than or equal to r, since this open ball Bxr contains all those points which are less than r distance from the point small x. So, since y is an element of a1 by n, y will not be contained in this open ball, and hence d of xy, the distance between x and y, will be greater than or equal to r. Consider the set a1 by n union singleton set x. Then the distance between any two distinct points of the set a1 by n union singleton set x is at least 1 by n, and thus we have obtained a superset of a1 by n having the same property, that any 2 points of the set are at least at a distance 1 by n apart. This contradicts the fact that a1 by n is maximal with respect to this property. This is a contradiction. Hence, Bxr intersection with a1 by n must be non-empty, which will imply that Bxr intersection with D is also non-empty, since D is a superset of this a1 by n. Therefore, D is dense in X, and this implies that X is separable, and we know that separability implies second countability. So, X is second countable. This completes our proof.